Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 5th, 2025, about 4 days ago. It introduces a training strategy called selective gradient masking that corrals risky knowledge into a small slice of the model so it can be carved out later, and this localized knowledge then takes about 7 times more fine-tuning steps to relearn than with a standard unlearning method. The paper is titled Beyond Data Filtering, Knowledge Localization for Capability Removal in LLMs, and as we will see later, the implications for how we train and safely edit large models are quite significant. Alright, Figure 1 gives the first concrete payoff. Selective gradient masking moves the model to a better trade-off between forgetting biology and keeping everything else. The left panel plots general knowledge performance against biology loss and shows the orange selective gradient masking curve sitting consistently above the blue filtering curves at the same retain loss. The right panel repeats this for biology-adjacent fields like medicine and chemistry, and the pattern holds. The gray no-filter runs stay lowest on biology loss, meaning the model preserves biology knowledge instead of removing it. Well, Figure 2 shows how selective gradient masking carves each transformer block into forget and retain parts. The orange units mark the forget segment, which learns from data that should later be removable. The gray units form the retain segment, which preserves general capability even if the forget slice is zeroed out. The zoomed MLP diagram highlights that only some neurons and connections are tagged as forget, so the method localizes risky knowledge rather than spreading it across the whole block. So, Figure 2 showed how the model splits parameters into forget and retain slices inside each block. Table 1 now spells out what happens for each data type during training. Forget labeled examples trigger mask gradients so only theta forget updates while theta retain stays frozen. Unlabeled data receives standard training which updates both parameter sets. Retain labeled data has the forget parameter zeroed during the forward pass, so only the retain slice learns to handle normal behavior on its own. Alright, Figure 3 tests whether selective gradient masking still works when many Spanish forget examples are unlabeled. The left panel shows retain loss on English, and the orange curve stays below the brown gradient routing curve across almost all undiscovered rates, so English performance is better. The right panel plots forget loss on Spanish, and here the orange curve stays highest, which means stronger forgetting. Even when nearly all Spanish examples are unlabeled, selective gradient masking keeps more English skill, while erasing more Spanish knowledge than data filtering or gradient routing. So while Figure 3 focused on accuracy trade-offs, Figure 5 turns to leakage, which means how much forgotten knowledge still seeps into the safe parameters. The left panel compares standard training to selective gradient masking and shows that matching the same forget loss would have required only about 1 million Spanish tokens, a tiny fraction of the 140 million total. The red leaked arrow marks this equivalent exposure. The right panel plots leakage versus undiscovered rate and shows that larger models, especially the purple 64 million model, consistently leak less than smaller ones. Alright, Figure 6 asks whether this localized forgetting can be undone by hostile fine-tuning. The left panel tracks biology forget loss as adversarial steps proceed and shows RMU snapping back to baseline within about 50 steps, while selective gradient masking and strict filtering take roughly 350. The right panel plots per token loss on biology, and the orange selective gradient masking curve shifts the whole distribution upward, which indicates broad weakening of biology knowledge rather than a few catastrophic mistakes. So Figure 6 showed that selective gradient masking resists hostile fine-tuning. Figure 9 now asks what that robustness costs in compute. The left cluster of bars shows that all 3 methods reach strong biology forgetting, with about a 95 to 99% compute penalty, meaning they need only a few percent of baseline training. The middle cluster reveals that selective gradient masking hurts related fields more than weak filtering, but less than strict filtering. The right cluster highlights the key trade-off. Selective gradient masking is about 5% slower on general knowledge, while strict filtering can even overshoot and undertrain by roughly 15%. Selective gradient masking shows that you can steer risky knowledge into a small, removable slice of a model, even when labels are noisy, and still keep most helpful capabilities. It also makes that risky knowledge much harder to relearn through hostile fine-tuning. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.